Okay, so this is the solutions to the homework from December 14th, 2011. We're working on related rates and trying to squeeze in some problems that find the rate of change of an angle. All right, so here's our first problem. Part A asks us to find the distance in kilometers between ship A and ship B when x is 4 and y is 3. Well, this isn't even calculus. All we need to do here is use the Pythagorean theorem. We know that x is 4, y is 3. Change my pen. So then part A, I can just simply say 3 squared plus 4 squared equals, and I'll call it missing distance z, since we'll just use x, y, z. So that's 9, 16 is z squared, 25 is z squared, so 5 must be z. So that's A. B, find the rate of change in kilometers per hour of the distance between the two ships when x equals 4 and y equals 3. All right, now we need to go back to the problem and see. I know that since this says rate of change, I'm taking the derivative of some formula that's going to lead me to find this rate of change. So if I notice in the problem, ship A is traveling west toward the lighthouse. All right, so its distance from the lighthouse right now is 4, but its speed is 15 kilometers per hour. And since it's going toward the lighthouse, its distance is decreasing. So that's going to be a negative value. And we represent a rate as the derivative of that variable with respect to time. That's what you always got to think of in your head. So this is a dx dt. So we have an x, and we have a dx dt. We also have a y and a dy dt. Ship B is traveling away from the lighthouse. We have a y is 3, so a dy dt, its rate is 10. We now know that z, the distance between the two ships right at this point, is 5. So we are being asked to find what exactly is the rate of change between the two ships. And that's what we're trying to find. So we're going to use the Pythagorean theorem again. And we use, x squared, y squared, and z squared. We've done this a million times, guys. So we have 2x. We got to write the derivative with respect to time, plus 2y, derivative of y with respect to time, and the derivative of z with respect to time. Okay, we know 5 out of those 6 variables, so let's plug and chug. 2, 4, negative 15. 2, 3, and 10, 2, 5, and our variable in question. Okay, if that was too fast or whatever, you can always go ahead and pause the video and catch yourself up. So all we're doing right now, we know that we need to find the rate of change. We have to take the derivative of our formula, and leaves us with 6 unknowns. We know 5 of them, and we're going to find the 6th one now. So 4 negative 15 is negative 60 times 2 is negative 120. 2, 3, and 10 is 60. And 10 dz dt. So negative 120 plus 60 is negative 60. So we divide both sides by 10, and we get negative 6 kilometers per hour is what the rate of change is. So the rate of change between the ships, the distance between the ships is actually getting closer because the rate of change is negative. So as ship A moves closer to the lighthouse and ship B moves away, that distance between the two ships is actually getting shorter. And if you could look at it, the evidence is kind of here. Ship A is moving a little faster, so as it's getting closer, faster to the lighthouse. And that is going to make that distance shorter. All right, enough of that. So B's done. C, let theta be the angle shown in the figure. Find the rate of change of theta in radians per hour when x is 4 and y is 3. So it's nice they didn't change up these values on us. We use the same things. Since now that we know x, y, and z, we could use any trig function we want. So it might be easier now to say if theta is, let me change colors here. If theta is here, it might be easier to say, let's use the opposite over the adjacent or over the hypotenuse. I'm sorry, and use the sine function because the derivative of sine is cosine, and that's going to be something that's a little easier to find. We don't have to deal with secants or anything like that. So the function we're going to use is sine of theta equals y over z. Well, we need to know what theta is first. Okay, so the sine of theta equals 3 over 5, and theta is going to be that of 3/5. So to 3 decimal places, theta is 0.644. So now that we know theta, we can go ahead and take the derivative of our original function and plug in our theta, our y, z, and dy, dt, dz, dt. Alright, so the derivative here, we got cosine theta, d theta dt, because there's a rate. We have a quotient rule. So we have z times dy dt minus, and sorry for the running into the other stuff here, minus y dz dt, so they kind of just trade off here, all over z squared. So some plugging in, we're going to find the cosine of 0.644 d theta dt equals 5 times 10 minus 3 times -6 all over 5 squared. So I'll just put 25. And we have on the numerator 50 plus 18 divided by 25. So I'm going to need a new page. I was trying to avoid it. Can't avoid it anymore. So I've got cosine of 0.644 d theta dt equals, what did I say, 68? Let's go look. 50 plus 18, so 68 all over 25. And then a simple division, so d theta dt is going to be 68/25 divided by the cosine of 0.644. Okay, so we work that out in the calculator. We find that this angle is increasing at a rate of 3.401 radians per hour. Okay, so does that make sense? Well, yeah, because ship A is moving in and ship B is moving out. So as that line changes, it's going to get steeper, 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 so that theta is getting bigger. All right, and make sure we have our label, radians per hour, and we're good to go.